Good morning, everyone. I have some good news and I have some bad news. Which one do you want first? Bad news is that this is the second to the last lecture of the semester. What's the good news? It's the second to the last lecture of the semester. I'm not going to make it today. It's just I'm not going to be able to make it through all the material today. So that means Monday I will be lecturing in lab, right? That will be the final lecture of the semester. I posted that grass will be starting at 8 o'clock this Friday, not to 7 o'clock. Some of you do like coming a little bit early. I have to go in and get an injection in my back. Steroids, yay! So I'm taking, procedure is at like 8:30 in the morning, so, and then the doctors tell me I'm not really allowed to move much or can't pick up objects and that kind of stuff for 24 hours. So I'm just not going to bother coming to work. But grass will be open, teachers will be on hand, tutors, all that sort of stuff. If you're looking specifically for me, begging for mercy, whatever it is you want to do, contact me via email, right? We'll meet at some other time, right? So just let me know. We'll make it happen. So that leaves Monday, final lecture, and then Tuesday, what are we doing? Review, because Thursday is exam, and then Thursday of finals week will be the autopsy. So our final is scheduled for Thursday at 9 o'clock. You have been programmed all semester long to get here at 9:30 in the morning, right? The exam autopsy starts at 9 o'clock, not 9:30, 9 o'clock in this room on the Thursday of finals week. And we don't do anything else that week, right? There's no lab on Monday, there's no lecture on Tuesday, right? So just plan on that, right? 9 o'clock. I can't say that enough. 5 of you are going to come in at 9:30. I know. I just know it. But that's all right. We'll figure that part out too. All right. Bananas. We had just started on kind of going through this chart, and the whole point of this chart is to give you a relative sense of kind of how radioactive things are. Because again, I'm trying to educate you in this idea that radiation is natural. It comes from natural places. It also comes from synthetic or human-made sources. But radiation is natural. For example, there's a banana, right? We talked about this. Sleeping next to somebody, living near coal power plants, right? And the daily background, like average background all across the United States, okay? That average background of radiation. And then flying from New York to LA, I mean, you might only do this a few times in your life, depending on your career, right? It's not dangerous because of radiation. It's safe and dangerous for other reasons, right? It's convenient, blah, blah, blah. But the crews, right, on these things where it's their everyday job to be in this high radiation environment are kept track of, right? But even for long-haul flights from coast to coast here in the United States, there's no limit on the number of hours they can fly in a year. It's those long flights that are 12 to 14 hours where the pilots have to be really careful with their radiation exposure and the crews. All right, so again, as a matter of scale, we're going to go to the next scale on this chart. So we've kind of seen what the blue is, right? And we're going to take all of the blue, every square on this chart, and we are going to squish it down into those 3 green squares. So those 3 green squares mash together every single one of those blue squares we just talked about. Add together all those exposures, right? So all of that together, living in a stone, brick, or concrete building for a year is equivalent to all of this. What's wrong with stone, brick, and concrete? It's radioactive. Where does stone, brick, and concrete come from? The ground. The ground is radioactive. Okay? So, okay. Let's start this conversation. It's going to be going for a while. 3 Mile Island, Chernobyl, Fukushima. The known, very public nuclear, I will use the word accident very loosely for what happened at 3 Mile Island, okay? Prior to 3 Mile Island, which happened I think in 1973? Anyway, something like that, okay? What's that?
What is that?
What?
Yeah. If you have time to tangent on that. I know, I'm sorry.
3 Mile Island is the reason everybody is scared of nuclear power now. Prior to 3 Mile Island, nuclear power was like, yeah, let's nuke them. And after 3 Mile Island, nuclear, bad. 3 Mile Island was in New Jersey? Pennsylvania, thank you. Well, it is Pennsylvania, New Jersey, New York. It's all the same thing, okay. And so it was a nuclear power plant that had a problem. And the plant did exactly what it was designed to do to prevent a meltdown. And it did it. And as part of that procedure, the operators were forced to allow radiation to be released in the form of radioactive steam as a way to control the temperature in the reactor. All of it was within the guidelines set by the Environmental Protection Agency and the Nuclear Commission and all that kind of stuff. Well, guess what happened when the press caught wind of a meltdown at a local nuclear reactor and a release of radiation? The media went berserk, right? Because the media doesn't have anything else to do apparently. So this was the average dose that people received during the accident if you lived within 10 miles. Equivalent to all of that and barely more than living in a brick building for a year. Okay? Here is what the EPA says can come out of a nuclear power plant over the course of a year. Safe levels of radiation coming out of a nuclear power, if necessary. It's not always, it's just in the event that you need to do something that causes radiation, this is safe, okay? This is the yearly dose from potassium in your body. Why are we freaking out over that when this is bananas? And you get potassium from other sources, right? Do you see the problem that I'm having with the nuclear oogie boogie? Right? People are afraid because we don't understand. I give that to the general public, right? Scientists are terrible communicators. We went to science to avoid English, right? Okay? And so we tend to use big words because they are accurate, right? The word describes exactly what, but that leaves the general public feeling stupid or condescended to or whatever, right? And so it can come across as arrogance, and it is arrogance. It can come across as superiority, and it is superior. Like, scientists historically have done a terrible job of communicating to the general public what's going on. Which is why bananas was such a good idea. Until the banana lobby killed it, right? So, so here is the limit set by the Environmental Protection Agency, right? That a single member of the public, now public means someone who is not in a nuclear industry, okay? So somebody who normally would not be exposed to radiation, this is the legal limit. This is what 3 Mile Island did to people within 10 miles. This is the legal limit. Okay? Here's the maximum dose from the 3 Mile Island incident. So there were variations in dose, right? But even still, it was not the environmental catastrophe that it was portrayed to be. And it's since 3 Mile Island, the public perception of nuclear power has gone like that. Fukushima. We'll talk about Fukushima in a minute. But following Fukushima, Germany began a process of decommissioning its nuclear reactors. Because again, the media's portrayal of what happened at Fukushima, right, and the stuff that got released, blah, 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 scared the public and the politicians into an action that they now regret. Because what is Germany now doing? Spooling the reactors back up again. They're going to save themselves a lot of money. We'll talk about why they're spooling their reactors back up again. It has to do with Russia. Here's a mammogram. Okay? To my genetically female friend. Men do get mammograms too, but generally it's women, right? Let's have a little talk for just a second. You may not be aware of it, and your doctor may not be aware of it, but the American Medical Association guidelines for mammograms changed about 15 years ago. Prior to that, they were recommending mammograms to women over the age, if you had no history of breast cancer in your family, over the age of 40, get one every 1 to 2 years. The current guideline is to only get one once every 10 years if there is no history of breast cancer in your family. If there is a history of breast cancer in your family, talk to your doctor, because the guidelines are different depending on what they know about your ancestors, okay? And what kinds of cancers was and how, whatever, right, okay? The thing is they discovered that with regular mammograms for women who were not predisposed to breast cancer, it was inducing breast cancer. Okay? Why? What's going on? You're doing a bunch of x-rays. Where? Right? Right in the chest, where there's a lot of organs that are very useful. Right? And so it's a risk that the American Medical Association decided wasn't worth it for women who don't have a history of it. Right? If you have a history, get on top of it. Right? If other women in your family are predisposed to it, get on top of it. It's useful. It's a very, I've been told, very uncomfortable process, but medically useful to preserve your life. That being said, sometimes we get too excited about things, right? So if your doctor is recommending a mammogram every year after the age of 40, and you go, why? And they go, because, have a conversation with your doctor, okay? Because it may not be necessary. Okay, so, this is a 1-day dose between 2 different sites, okay, after the Fukushima disaster. So you can see, I mean, people could be walking around in mammogram territory, right, okay? But notice they qualify this, right? Most areas saw barely elevated doses. There were places around Fukushima that were barely registering as several bananas, okay? But this is like kind of a sort of a 2 different sites measuring this thing, right? Here's your normal background. Here is a CT scan of your chest. Again, lots of x-rays taken over and over and over again, okay? This is the dose you get from 1 hour standing near Chernobyl in 2010. Chernobyl happened in 1986. Yearly dose, 1 hour. 3 Mile Island average dose, maximum from the 3 Mile Island incident. This will persist for the next 50,000 years. How much more serious was Chernobyl compared to Fukushima and 3 Mile Island? Order of magnitude does not even begin to explain how much worse Chernobyl was. So this is the EPA limit that a single member of the public can get. Here is your limit if you are a radiation worker. Yearly limit.
That's a lot.
That's the year. So we're just radiation workers, just throw them in there and good luck and, you know, thank you for your sacrifice in society. No! This is safe! If you get it in a year. How long would it take this to equal this? Like what, 5 hours? 6 hours? That's the problem, right? Working in a lab that does radioactive isotopes, right? You can get, like this was my limit when I was working with the uranium in graduate school, right? Do I have problem? Don't answer that.
Because of the uranium.
Because of the uranium? No. Right? Okay? So, okay. So, take all of these green squares, add them all up together, and you get that many orange squares. Okay? Just as a scaling factor. So those squares right there are all those squares right there. Do you see the scaling factor here? Okay? This is where it gets, this is the scary slide. Okay? 1 year dose clearly linked to increased cancer risk. This is the legal limit if you're working with radiation. Here's what you need in order to have an increased cancer risk. If you're working doubles, right? No, because you're not allowed to work doubles like that, okay? This is what you need in order to get radiation poisoning, okay, if it's received in a short time. Here's a sometimes fatal, okay? Here is severe radiation poisoning, and you might survive if you get prompt treatment, and here you're dead.
That's a lot of squares.
Compared to the legal limit. Okay? This is where it gets really dark. Warning you. In this box, this is the dose limit for emergency workers if you are protecting vital equipment. This is enshrined in the law. If you are working to keep that nuclear reactor from doing something worse, if you are trying to fight a fire on a building that contains nuclear waste, like if you are in a role where you're performing emergency operations, okay, then the U.S. government says it is okay, it is legally okay to run the risk of a slightly increased risk of cancer if you're protecting property. If you are protecting life, what scares me, I'm not sure what scares me more. That this is enshrined in law as acceptable legal limits, right? Or, no, that's what's actually disturbing. Wow, right? Take all of the squares combined that I have showed you. Every single square. Add them all up, okay? This is what you got 10 minutes next to Chernobyl right after the meltdown. Every single one of those yellow squares is the entire chart, that many squares put together. And that's what Chernobyl was immediately after the meltdown. It was bad. We're going to talk about exactly how bad, but if you want to know what your personal exposure to radiation is on average based on statistical analysis, you can go to the American Nuclear Society, ans.org, and at the top you just click on the thing that says dose chart or whatever, and it will be an interactive thing where you say what you do, blah, 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 you know, I smoke, I don't, whatever, right? But like, notice cosmic radiation, depending on your altitude, you'd put a number in. If you live in Colorado, you're dead. Power plants, internal radiation, they just fill this in for you because of radon, it's just set. Jet plane, how often do you do that? Do you go past the x-ray machine at the airport, right? Do you smoke half a pack of cigarettes every day of the year? You gotta add 18 to this list. Because again, you're putting radioactive substances into your bloodstream, okay, right? Having a smoke detector, and then you put in all your medical diagnostic tests. Anyway, right? You can go calculate sort of an average that you would get exposed to in a year to see what's normal for you. Probably won't help you ever, but you know, is what it is. Okay. Finally, the end of chapter 31. I'm not going to make it. It's not going to happen. So we'll finish it up on Monday. So before we get to disasters, let's talk about how disasters can take place. And before we can do that, we've got to talk about what's going on inside of nuclear reactors. So this chapter is two parts. It is how do reactors work and how do you make bombs? So the answer is pretty close to the same idea, okay? But we are going to talk about two processes, nuclear fission and nuclear fusion. Fission first. Fission is the splitting of an atom. Typically, you take, for fission to occur, you need a nice, heavy, big, fluffy atom like uranium. Uranium's really good, plutonium's even better, okay? Uranium-235 is the isotope of choice for nuclear power plants. Plutonium, uranium-235 also for weapons, but plutonium better for weapons. Anyway, if you take a big fluffy nucleus, which is naturally unstable anyway, right? And you send in a fast-moving neutron, what you end up doing, it's like the neutron that broke the camel's back. It's got a lot of kinetic energy, it comes barreling into that nucleus, and what it does is it causes this fission to take place. The nucleus splits. And as it splits, it releases energy, thermal energy, it releases more neutrons, which also have a high kinetic energy, and those neutrons, 1 to 3 of them, are going to go find other nuclei, right? You don't ever have just a single nucleus sitting around. You got a lump of uranium-235, there's trillions upon trillions of atoms in it, right? And so these neutrons that come out of the fission reaction are going to go find other nuclei with which to hit, and they're going to hit, and they're going to generate more free neutrons, which are going to go get more nuclei, which are going to and this is called a chain reaction. Okay? So really the difference between having a power plant and having a bomb is how far and fast you let this chain reaction take place. An explosion, right, would mean that this reaction has gone critical. It's going so rapidly that the amount of energy released per time is very, very large. The time's very, very short. In a nuclear power plant, ideally, we don't want that to happen, so we want to make sure that the chain reaction is contained or limited in some way, shape, or form. And I want to be very clear. We're going to talk about reactors here for a while. I want to be very clear. Reactors everywhere across the surface of this planet, all of them are designed to not be bombs. In other words, there isn't enough material in the reactor, in the fuel rods, for it to explode as a nuclear explosion. Chernobyl exploded, Fukushima exploded. Those were conventional explosions. I'll talk about why they happened later. But to be very clear, you cannot turn a reactor into a nuclear bomb. You can turn it into a conventional bomb, but you cannot turn it into a nuclear bomb or fission weapon. It's just not going to happen. There isn't enough of something called a critical mass in the reactor for it to happen. So we'll talk about what can go wrong, but there are parts of a reactor that I do want you to know, and I'll probably test you on, okay? Because I think this is really, really important information, not to have for physics class, but to go out and be informed members of the public when it comes to understanding why nuclear is so contentious and why it could possibly save us as a species, but also doom us as a species, depending on how we work with it. So reactors need material, they need fuel, okay? Most often uranium-235, sometimes plutonium, but most often uranium-235. Plutonium has to be made in something called a breeder reactor. You need a uranium reactor running, and then you can actually make plutonium-239. Again, it's outlined here, right? It's a synthetic, it doesn't occur in nature. You need the material, you need something that moderates the reaction. And moderator doesn't mean controller. That's what control rods are for. Moderator means you need something that can take the energy that's coming off of these fission reactions and safely transfer that energy to the outside world. So a moderator in the United States typically is water. We're using the fuel in order to boil water, make steam, and we use the steam to turn turbines. In other reactor designs in the world, moderators are carbon and water, like carbon bricks with water flowing around them. But the job of a moderator is to extract the thermal energy that the reaction is producing and get it somewhere where it can be used to generate electricity. The control rods is where everything is at. From their name, what do you think they do? They control the reaction. So control rods, you can see like you've got fuel rods, and this is a schematic. This isn't exactly how they go together. But you've got fuel rods and then you have control rods. The moderator surrounds everything, trying to capture all of this energy. Control rods can be inserted or pulled out, okay? And the distance, the amount that they're pushed into the reactor or pulled out of the reactor determines how fast that reaction is going to be taking place. That's because control rods are made of materials that are like sponges for neutrons, okay? They can't affect like the fission itself. A control rod can only soak up neutrons. And so if the control rods go all the way into the reactor, all of those neutrons that are coming off of those fission processes, they get sponged up, they get sucked up, they get captured by the control rod, and they're not available to go on and cause fission, and actually the fission just sort of shuts down. If you pull them all the way out, then nothing is absorbing those neutrons that are coming out of the fission reactions, and you start getting a rapid rate of reaction. And so plant operators are trying to balance on a real-time basis like how much the reactor is producing energy versus the requirements of the electrical energy they need to put on the grid. And you can actually change, right, the output of that reactor. There are efficient modes to run in, and there are less efficient modes to run in. You can actually poison your reactor if you're not careful with how you control it. Poisoning in this sense means that you shut down the reaction to the point where restarting it is a big pain. So there's lots of stuff that's going on in there. But the bottom line is that it's the control rods that are really in charge. Moderator captures energy, fuel rods provide the energy, control rods soaking up those extra, sometimes they're called thermal neutrons, but they're capturing those neutrons and preventing it from taking, not allowing the fission process to continue because the neutrons can't run into other nuclei to cause them to split. You're seeing a couple pictures here. We'll talk about the one on the left in a second. The one on the right is the picture of a reactor when the lid has come off, okay? I don't know if you can see, but do you see how there's some bright white circles right there? They've just pulled a fuel rod out of that circle and they pulled it out. You can't see it. And that one's been removed and that one's been removed. This is a research reactor, so-called because it's actually actively used to test different scenarios and all that kind of stuff. Typically a reactor operates with its lid closed because you're trying to boil water into steam and it's a pressure vessel. And you want to keep that pressure inside the reactor. But during servicing or research or anything else, they might run with it open. This is a production reactor that generates electrical power for the grid. Again, with its lid off, they are actively removing fuel rods. So the fuel rods get inserted into these casements right here, and then this device comes down and clamps onto it and then pulls it out. Some of these other things are in there reaching down to pull the fuel rods out and put more fuel in. Have you noticed something in common between the two pictures? The blue glow, okay? That is real, okay? I've seen this glow. It's called Cherenkov radiation. It is the glow that results from nuclear particles, alpha, beta, gamma, a bunch of different things, that are moving through the water faster than the speed of light in water. Now, I've told you that the speed of light is the maximum speed limit in the universe, right? When we say that, it's the speed of light in a vacuum that is the maximum speed limit in the universe. But as we studied in optics, when light goes into a material, it slows down, right? So it's possible to exceed the speed of light if you are in a material that's not a vacuum. Boats do this all the time. Not the speed of light. They exceed the speed of water waves in water. The speed of a water wave in water is like 10, 12 miles an hour. So as soon as a boat goes faster than that, it gets up and forms a wake, a sonic boom in the water, which you're seeing is the optical equivalent of a sonic boom, created by a particle that's moving through that water faster than light can move through that water. That blue glow is the result of those faster than light particles in that medium. And they are produced because of the radioactive decay of those fuels. All right, what's the picture here on the left? You're looking at the lid, the topmost part of the world's first nuclear reactor. This reactor began its journey at the beginning of the Manhattan Project. This is a picture of Enrico Fermi, who was an Italian Jew who fled the rise of Mussolini in Italy and came to the United States in the 1930s. He was a nuclear physicist. He was studying these nuclear processes and was one of the first scientists to be involved with the Manhattan Project. About a year into the Manhattan Project, Fermi was tapped to not only help with the bomb project, but to see if there was a way to use the understanding of the fission process in peaceful applications, generation of electricity, demolitions, that sort of thing. And so he started building the world's first nuclear reactor. Now, if you've been asked to head a top secret program that you don't even want your allies to know about, Great Britain would not know about this project until the day they were invited to see it turned on for the first time, okay? Top secret, like nobody can know about this except a few people in the United States. and you had to pick a place to hide something that is roughly 3 times the size of this room, where would you go? Desert? No, nowhere? Okay, that's what the Manhattan Project did. Right? They're going to develop a bomb, nobody can know about it. Let's see, where can we go? We're going to need a lot of space, and we don't want to be near anybody because if something goes wrong. Desert, Western United States. Nobody lives out there. Right? And just a bunch of deserts out there, right? And all that kind of stuff. And let's see, we are going to need 12 Nobel Prize winners, about 2,000 engineers, about 5,000 mathematicians, and secretaries and support personnel. Somebody needs to make coffee and food. Middle of nowhere. Let's just drop about 8,000 people overnight in the middle of nobody will know what's going on, right? No. So that was the Manhattan Project, right? Something obviously was up at Sandia in northern New Mexico. Fermi took a different direction with this, and he built the world's first nuclear reactor in the racquetball court underneath the football stadium of the University of Illinois at Chicago, because that's where he was working. He was at the University of Illinois at Chicago, and the racquetball court nobody was using. It had been not used for several years. You want to hide something from everybody? Put it under the football stadium. Why not? Right? They had to discard. So his reactor was made out of, his moderator was graphite bricks. So what you're seeing here is a bunch of different graphite bricks with places for them to insert rods and stuff like that. They were kind of big bricks too. How do you get like 56,000 graphite bricks all delivered to somewhere without anybody going, hey, what are you doing? Well, they pretended, but they had them delivered over a series of months. Different deliveries of different sizes, right? So that nobody would, no one delivery would elicit suspicion. And so they built it slowly over a series of months. So no pictures of this were taken. It was that top secret. So this is a artist's depiction based on the descriptions that people who were there when the reactor was first turned on. This is Fermi right here. Okay, manually inserting control rods. This was a research reactor, right? They just wanted to see if it was possible. Again, it was impossible for this thing to blow up. There was not a critical mass in this reactor, right? They were just trying to see if the reaction could sustain itself. They were having a lot of trouble getting the reaction to actually continue. It would kind of sabotage itself as it went with different byproducts. Anyway, scientists all gathering around, Fermi inserting, he wasn't the only one, there were other people inserting them in and out. Things to measure what was going on, and then about 20 people were invited to come and witness it, including the British, a lot of American, a couple people from Congress. Anyway, the British weren't very happy, but they were invited. By the way, it worked. Spoiler alert. So back in the day, there was no like coded communication. Like you couldn't encrypt information very easily. And so what they did is they sent a coded message to Roosevelt at the time, President Roosevelt. And the message was this: the Italian navigator has landed in the free world and has found the natives friendly. Wow. Who was the Italian navigator? Fermi, right? Okay, what was the new world? The nuclear age, right? And the natives being friendly? It didn't blow up. Everything went okay, right? Like it worked, right? So, yeah, there's a piece of history for you, right? I am going to use a term very loosely. Modern reactors. No reactor has been built brand new in the United States since 1976, I think, 1978, until last year. when the first modern reactor very nearly finished. I think it's commissioning right now, okay? But there was almost a 40-year hiatus on the building of nuclear power plants, in large part because of 3 Mile Island and public opinion about nuclear power. Which means the power plants we have operating in the state of California, of which there is 1 remaining, one down near Morro Bay, San Luis Obispo, the Diablo Canyon power plant. They are all designs from the 1970s. Do you want to just hazard a guess as to maybe that we probably found safer ways of doing this in the last 40 years? Yes, the answer is yes. Okay, but because of idiots in Congress, it's been hard to make them safer. I'm, of course, not giving opinion, that is a fact. There are idiots in Congress. All right, so what does a quote-unquote modern reactor consist of? The part of a power station from the heat exchanger this way, the turbines and generators, is all the same whether it's coal, natural gas, or oil. Every single one of those power plants produces electricity the same way. They boil water, they use the steam to turn a turbine. They recapture the condensed steam and put it back in the heat exchanger, but the heat exchanger's role is to do what it says on the tin. It exchanges heat from the thing that's causing heat to the stuff that's generating the electricity. In the case of a nuclear power plant, that heat is generated by those fission reactions, captured by the moderator, which in the United States is water. Water is in every heat exchanger all over the world, but sometimes there's carbon bricks in here. That steam and boiling water, okay, gets circulated into the heat exchanger. Where? And to be clear, that water never comes into physical contact with the water that's in the steam turbines, right? The whole point of a heat exchanger is to allow thermal energy through, but not allow physical contact. The radioactive water is contained in this loop. It flows around and around the reactor, cooling off in the heat exchanger, heating up the boiler, okay, and then gets pumped back in to be reheated in a never-ending loop. The amount of radioactive material, whether it's in water or anything else, is so strictly controlled in a nuclear reactor. I think I've shared this with you, that olive oil is 20 times more radioactive than what you're allowed to send out of a nuclear power plant. Like, yes, okay? Olive oil is radioactive. Why is olive oil radioactive? Because it's Italian. No, because it comes from dirt, right? Olive oil comes from olives which grow on trees which are in the dirt. Living things are radioactive. It's just everywhere, okay? So, and I can't tell you how much this stuff has never gotten out, except for 3 times. There's only 3 times that radioactive water has gotten out of a nuclear power plant. And what are those 3 times? 3 Mile Island, which was very controlled. Chernobyl, not controlled at all. And Fukushima, controlled. So, the Achilles heel for any reactor, nuclear reactor, are these pumps right here. This one, sort of. This one, definitely. Because if you're going to have a problem in a nuclear reactor, it's going to be with the pressure vessel side. This is a pressure vessel. This is all pressurized. This is also pressurized. But if you let this out, it's just hot water, right? Let this stuff out and you've got radioactive steam going everywhere. Reactors, 1980s and before, all of the designs are such that if these pumps stop working, there is enough thermal inertia in the system, enough nuclear fission can continue that the water will boil to the point where it exceeds the pressure rating of the pressure vessel and you will have a steam explosion. When a reactor goes into its shutdown mode, these pumps must continue. If those pumps stop moving water for more than a couple of minutes, you are very likely to exceed the design parameters of your pressure vessel and you will have a conventional pressure explosion. What must never fail in a nuclear reactor? The cooling pumps. That is why there are backup systems in place in every nuclear reactor design that ensures that no matter what else is going on, those pumps keep going. Part of those backup systems include diesel generators that kick on, burning diesel fuels for hours and days at a time to just keep the cooling pumps moving. If the rest of the power plant loses electrical energy, those pumps will continue to run. More modern designs are made such that coolant flows by gravity. So even in the event that the pumps stop working, gravity flow is sufficient to maintain cooling for at least 72 hours, which is enough time to get in there and hook up systems that will then allow cooling water to flow. Okay? But anything made before the 1980s does not have that design in it. You are looking at the roof of reactor number, I don't remember, 4? No. 4? 2? I don't remember. Doesn't matter. At the Chernobyl nuclear power plant outside Pripyat, Russia, on April 28th, 1986. 1982. I'm not good with numbers, but I'm in the ballpark. Okay? You can look it up. Approximately 1 o'clock in the morning, some, I'm guessing mostly drunk Russians because it was 1 o'clock in the morning in Russia. Not to dig on Russians, but there isn't much to do in the middle of nowhere, Russia, except get drunk. So witnessed, well, they heard an explosion coming from, so Pripyat was a town that was situated a couple kilometers away from the Chernobyl plant, where there were several reactors all providing electricity for Ukraine and parts of southern Russia. And they heard an explosion, and they turned to see the power plant on fire. And they would later tell people that, yeah, it was really bright. What had happened, how much time do I have? The short version is that Moscow ordered the plant to do something that it wasn't designed to do, that the plant operators knew was unsafe to do, but in a crumbling system of government that didn't take no for an answer, there was only one thing to do, which was do the thing that the higher-ups said to do, even though you told the higher-ups that it wasn't a good idea to do. Because if you didn't, Siberia was the next stop for you and your family. I am not exaggerating that. I have spoken to Russian scientists about the culture that existed in the Soviet Union before its fall, and that is how they described it. These same scientists were ones that I met at BYU who had come over as part of like a sort of an exchange. We'll send you some of our scientists or some of yours kind of thing in the name of international peace. I remember when that scientist got off the plane. We had driven up to pick him up at the airport and back. He came off the plane in what obviously he considered his best clothes. White shirt, tie, slacks, shoes. Frayed at the cuffs, like you wouldn't believe. a tie straight out of the 1970s. Shoes that hadn't seen shoe polish in years. We didn't call it out, we didn't make fun of it, but it was very obvious that this scientist did not have money. We got him to the campus place where he was going to live, and he basically almost started crying. And one of the teachers pulled him aside and said, "What's going on?" And he, in broken English, described to us that he'd never seen a living spot so clean, so beautiful, and he wished his family could see it. We later found out that this guy has a PhD in nuclear physics, smarter than all get out, really accomplished in the scientific field, could barely feed his family on the money that he received from the Soviet government. Like, it was, we all went out and bought him clothes. We felt so bad for the guy, right? And it broke our hearts. And he would tell us things like that. He was very embarrassed to, but we could finally kind of dig it out of him about what was going on. And at Chernobyl, it was kind of no different. To be clear, he never worked at Chernobyl. He worked at other plants that were Chernobyl-like. But he said this thing, the way that the economy functioned or didn't function, the way that government dysfunction was, the fact that you couldn't say no just drove you to do things that you knew shouldn't happen. And that's what happened at Chernobyl. We had a speaker come once that was part of the IAEA, the International Atomic Energy Agency. And he was one of the inspectors that went to Chernobyl to inspect after the disaster, trying to figure out what had happened because the Russians weren't saying. And he said that we found some of the early computers of the time, the systems that were designed to be the safety systems for controlling the reactor in the event of power spikes and things, they had been disabled because the parts in them had broken, they couldn't get replacement parts for them. And so to keep the reactor running, engineers had taken jumper cables and just bypassed the safety systems with jumper. This is how Chernobyl was functioning, okay, at the time that the accident happened. So a lot of physics about why the accident happened, but again, it was political in nature. It was stupid, okay? Not because the scientists there were dumb. They knew they were running risks and that what was about to happen was a very real possibility, and in fact it happened. About 1 o'clock in the morning, the pressure, the temperature, the power output of the reactor spiked and then dropped. And they thought everything was fine. 2 minutes later, it exploded. The water that was the moderator had entirely flashed to steam. Okay? The reactor had gotten so hot that there was no liquid water left in the pressure vessel. The pressure vessel exploded. The lid that was in the Russian design on the bottom ended up on top, okay? And the core itself was exposed to air. The radioactive steam release was bad. The chunks of graphite that were used as part of the moderator were raining down outside the plant. The fire was raging inside of the reactor area. One of the byproducts of very rapid dissociation of water like that is hydrogen gas. So there were hydrogen explosions going off and hydrogen was burning. The fire department showed up about 40-ish minutes after the explosion, and they pulled up, and the firefighters mentioned that they thought it was strange when they got out of the fire truck that there were so many smoking bricks all over the ground. You know, the plant was made of rebar reinforced concrete panels, but why were there? Those were the moderator. Chunks of uranium fuel and control rods still inside the bricks, right? To this day, the suits that those firefighters wore as they started dropping like flies with nausea, vomiting, diarrhea, and were rushed to the Pripyat hospital, the hospital, local hospital, had been trained on how to treat radiation emergencies because they were right next to a power plant. And so they saw instantly what these firefighters had been exposed to. They knew it was radiation. They put them all in a room in the basement and stripped them of their clothing. That room is so hot today of radioactivity, it is crazy. Okay? They just stripped them down, washed them off, and sealed the room. The room was a total loss because of the radiation that was in it. The bravery of those firefighters, the bravery of the plant operators, some of them refusing to leave. The person that took this picture died because of radiation exposure. The pilot of the helicopter also died because of radiation exposure. It was a disaster. All the parts of your reactor that you never ever want to see the light of day saw the light of day. You are looking at the aftermath of the fire, but do you see that kind of very slight curve right there, that kind of whitish? That's the edge of the lid of the reactor, sitting right there. This is a valve underneath the reactor. Do you see the strands of stuff that are like right here? Okay, it looks a little bit like hair or spaghetti. For reference, this is about an 18-inch opening. About like that, okay? That is melted carbon, uranium, and cesium, control rods are made out of cesium, material that had turned into lava and had flowed, okay? It's called the China syndrome. It's called the China syndrome because here in the United States, if you have a reactor and you have, it's gone critical and it's melting, it's generating so much heat that it's turning into molten uranium fuel. There's nothing to really cool it down, and so it's on its way to China. Just burning its way. Have you ever seen Alien? When they cut the acid blood and it starts dripping through the deck? Like that, okay? This stuff luckily pooled and cooled on the cement foundation of the reactor, but it was in meltdown. True meltdown, okay? This is a map of the dispersion of radiation due to the steam and other particles that were ejected into the atmosphere. As you can see, weather patterns are very complicated because the black dot is where Chernobyl is and all of the orange is where the irradiation got to, including Scotland and parts of Ireland, where to this day you cannot sell from certain areas in Scotland, you cannot sell your mutton, your sheep meat, at the local store because it's too radioactive. Sheep are fine, no glowing wool, but the amount of radiation in the sheep, because of the radiation that deposited itself in Scotland after the Chernobyl disaster, and the sheep, of course, eat the stuff that's grown out of the dirt. The dirt contains these elevated levels of radiation. They exceed the United Kingdom's stipulation for safe human consumption. What do you do to contain a problem of this magnitude? The answer is you bury it. This is the sarcophagus. This was the initial structure that was built to contain the intense radiation that was coming out of the core. This was not something you could clean up, per se. This was something that you had to shield. We are going to have to shield this place for the next 60,000 years. How long have humans been talking to each other, like with anything that could even remotely be called a written language? About 5,000 years. How are we doing at reading the ancient hieroglyphics of the, right? This is everything you see in this picture is not allowed to leave because it's too radioactive. It must remain within the exclusion zone. The exclusion zone is a zone of, I think it's 50-kilometer radius around the reactor itself. You are not allowed to go inside that zone unless you are being escorted. There is now tourism allowed inside of that zone. You can pay to have a tour guide take you into Chernobyl. I would like to go. It would actually be pretty interesting. And there's lots of places within the exclusion zone that are perfectly safe because you can clean the roads, you can do all this kind of stuff. They took the top 12 inches of dirt everywhere and scooped it all up and put it in a huge pile and then sealed it off, right? Like just to try to get to dirt that wasn't as radioactive. But the metal, the tractors, the construction equipment, everything that goes into the exclusion zone stays. Because it's too radioactive to come out. This sarcophagus, okay, so here's sort of like the engineering problem you've got, right, okay? You've got a reactor in meltdown. So this orange stuff, okay, this is basically like all of the nuclear fuel that got deposited in various places. There's the reactor vessel and some of the stuff, right, okay? And so they're trying to contain everything that's been irradiated in here by putting this structure around the outside of it, right, okay? It was a steel reinforced concrete structure. Wall thickness was approximately 1 meter. Some places a little bit bigger, but no smaller than 1 meters thick, okay? About a decade later, the inspections were scheduled to see what was going on inside of the sarcophagus. Of course, too radioactive for people to go inside there, and so robots were thrown in. This is why we're all going to die to robots. NASA volunteered a couple prototypes that were made to go to Mars. One of the things that people aren't aware of is that the robots we send to Mars have to be hardened against radiation. They have to survive approximately 6 to 8 months in interplanetary space, exposed to the full brunt of radiation from the sun. So the processors, the wires, the memory, everything in their computers is hardened against the radiation of outer space to be able to survive the trip to Mars, and then on the Martian surface is actually pretty radioactive because the Martian atmosphere is very thin. And so they just have to be, and the moon everywhere, right? You need to be shielded from radiation. The prototypes went in. They lasted about 20 minutes. In that 20 minutes, they are able to get pictures of some of the insides of the plant. And in some places, the wall thickness had eroded to within centimeters. Erosion caused by intense bombardment of radiation. The sarcophagus was failing. And so, a new one had to be built. And instead of a sort of rush job that the first one was, this new one was going to have several features. First of all, it was going to have the ability to be constantly maintained and monitored. It was going to have the ability to actually start the work of trying to clean up the mess that the first sarcophagus, and the hope is that sometime within the next 200 years, we will be able to actually remove the fuel from ground zero and contain it safely in a different spot, right? So this new structure not only would be able to be maintained on a continuous basis, but it would have machinery, cranes and other things in it that would allow the picking apart of the rubble and going through and starting to process the radioactive and separate it out and all that kind of stuff. But it would also be able to move. It's the world's largest mobile structure ever. This is it in 2013 when construction began. Here it is in 2016 as the outer shell is it's becoming watertight sort of at this point, okay? It would move on rails to drive itself. So it's being built over here because it's too radioactive to go close to that thing. But it can move itself across, and it basically parks itself about halfway over that structure, okay? And then seals down, like it kind of settles and clamps. But it can then be brought up and moved back if necessary, right? To be able to do work on it and things like that, okay? Here it is in the winter of 2018, and that's its fully constructed, fully in place containment structure 2, okay? For keeping the radiation inside instead of outside. Again, this project's design is to last 100 years through constant maintenance. The hope is sometime in that 100 years we figure out a better way to do it, right? And just keep doing that. Because there really isn't any other choice. Barring some miracle technology that we find, right? To deal with it. Prior to 1986, how close did I get on the date? Did anybody look it up?
April 26,
1986. So not 22nd or 24th, 26, 1986. You think I'd be able to remember all those things? So this is the cafe in Pripyat. This is the coffee shop. This is the Starbucks, the place where people went, right, to get their coffee in the morning. I mean, pretty roses, right? Model Soviet town of the time. Kind of, you know, the central government's in decay, but everything on the surface looks good. And, I mean, it's got kind of that 1970s nuclear bombs are going to hit us aesthetic, but you know, it's nice. I mean, walk around campus, right? Every building looks like a bunker. Welcome to the 60s, right? Like, it's the way it was. 10 years later, that same cafe, because humans are not allowed to be there. And so nature is taking its course, right? Okay? 20 years later, look at what has happened. Chernobyl is a horrible incident. It is awful, and we will be paying the price for the next 50,000 years for this problem. But approximately 20 people died. Thousands more were displaced. Thousands would have their lives cut short due to cancer. I'm not saying there weren't effects. On Monday, you're going to learn exactly how many people have died generating coal power. And you're going to be surprised. But Chernobyl has afforded us something. It's a laboratory for what happens when humans are not allowed to be in an ecosystem. Wildlife didn't just survive, it exploded. There were birth defects and all kinds of things, but the organisms that made it passed on those traits that allowed them to survive. And now you have deer and fox, the gray wolf, long thought to be extinct in this part of Russia and Ukraine, the Pyrenees Mountains, came back. Nobody reintroduced it. But because humans weren't there to shoo them off or hunt them, they came back and are flourishing in the exclusion zone. We used to think that it was going to take eons for our impact, the visible impact of humans on this planet, to be erased. It takes less than 30 years for a place to be unrecognizable. There are forests in Pripyat that are oddly straight, like the trees are all growing like in a straight line. Those are the roads. The trees have grown up through the asphalt in between the buildings. You're walking through a forest and all of a sudden you run into a wall, okay? Where the trees can't grow. The soccer field, like you can't see the place where people used to sit in the stands. Because there's a huge forest growing on that soccer field and the trees have uprooted like the stands, and the stands are up there. Like it's crazy how good nature is at erasing humanity's impact. With climate change, with nuclear power, with nuclear weapons, with the existential crises that face our species today, it is never a question as to whether or not the Earth will survive. The Earth will survive. The only question is, how long are we going to survive with it? Because the Earth has incredible ways to heal itself. And I will continue that story because we have to talk about Fukushima on Monday. And then I might even be able to get to the part where I teach you how to make a bomb. See you then.